Now we're going to talk about light and some of its properties, particularly in the area known as geometric optics. And in this formulation, we're essentially approximating light as a ray, and we're neglecting the wave nature of light. So a lot of applications for this would be like bouncing a laser beam off of a mirror. We don't really have to worry about the wave nature in most of those kinds of cases. We can just think of the laser beam as a ray, and it moves in a straight line until it hits the surface of the mirror, and then it reflects. However, to start, the initial estimate for the speed of light was done back in the 1600s by a gentleman by the name of Ole Romer. And during, the time of Galileo and before, it was really not known whether the speed of light was infinite or whether it was finite. And we just didn't have a good way of measuring it. But Romer came up with a very clever method. So since Galileo had very carefully tracked the motion of the moons of Jupiter that were visible through his telescope, astronomers had from that been able to build tables of predictions and times for when certain moons would disappear behind Jupiter. And Ole Romer reasoned that these times and predictions would be based on the average distance that Jupiter was away from the Earth. And if he could measure the time when one of the moons disappeared behind Jupiter at two different points in Jupiter's orbit, or really two different times in the relative positions of Earth and Jupiter in their orbits, one when the Earth was closer to Jupiter in its orbit and one when the Earth was further from Jupiter in its orbit, he reasoned that when the moon of Jupiter was eclipsing or being eclipsed by Jupiter, when the Earth was closer, that the times, the actual time of observation would be ahead of schedule on average. And if he did the opposite, when Jupiter was further away, the eclipse would be behind schedule because light would be reaching Earth sooner in the first case, and it would take longer for light to reach Earth in the second case. And so that was his reasoning. And it turns out that he actually was able to do this, and he was able to get within 20% of the currently accepted value, which is pretty amazing. Especially since they didn't have the greatest of clocks. Later, the most accepted method for measuring the speed of light since Romer's time, up until when we were using lasers and high sensitivity oscilloscopes and timers and clocks and things, was Fizeau's method. And so he had a gear that was turning, and he could adjust the rate of its turn, and he had a light source, and light would make it through the gear teeth on the way to the mirror, and then the rays that were directly reflected straight back would have to be, the wheel would have to be turning at a precise rate to let the returning light through. And if you could measure the wheel rate that allowed the light to come through, you could actually then measure when the light was supposed to hit it, and you could therefore measure the actual speed. So this was the rotating toothed wheel method. Okay. Light when it's in this ray form, light from a source like the sun is going to travel or be emitted in all directions, but each individual ray you can think of as moving in a straight line until it's obstructed by something. And it's these straight line rays that will hit your eyes that then form images. Okay, whether you're looking through a window or whether you're looking off of a mirror, the rays have to hit your eyes for you to see anything, just like sound waves have to hit your ears for you to hear something. The most fundamental principle of reflection. Okay, so this is the law of reflection. And the law of reflection states that when light hits a surface, okay, an incident ray is going to be reflected off of that surface at an angle with respect to a perpendicular line drawn to that surface. It's going to be reflected at the same angle with respect to that line as the incident ray was. So whatever the incident ray was, whatever angle the incident ray came in at, that will be the angle of the reflected ray. Okay, so the law of reflection says well, they have it right here. Okay, so the law of reflection says the initial angle is going to equal the reflected angle. Now, this perpendicular line, we're going to refer to this as the normal. Okay. Let me write that a little bit better. Okay. So that line is a normal. And the reason we call it a normal is because normal in mathematics means perpendicular. So it is the line that is perpendicular to the surface. Now this rule holds ubiquitously, okay? But it is especially apparent when your surface is macroscopically flat, like a mirror. Not just macroscopically flat, but microscopically flat as well, like a mirror. You can have macroscopically flat things like asphalt or concrete walls. And light does not behave like this macroscopically. But each individual beam does. And that's exactly what this next slide is talking about. So we have two types of reflection. We have what are called diffuse reflection and specular deflection, or reflection. And diffuse reflection is this kind of situation here where your surface is indeed flat completely. Your incident ray comes in, bounces off the surface, and exits at the same angle that it came in at. This is called specular reflection. And this happens on mirrors, bodies of water, when it's raining outside, and the water fills in the cracks in the asphalt and things like that. They start to act like a pretty highly polished mirror. Specular reflection is when the light coming in hits a rough surface, and each individual beam in that emitted light will obey the law of reflection at each individual point that it hits, but the overall net result is that all of the beams get scattered in different directions, and therefore your light essentially spreads out in all directions. This is why you can see a laser beam that hits a wall from anywhere in the room, from any angle, because there's always going to be some of the light that's reflected toward your eyes when it comes to diffuse reflection. So diffuse reflection causes the light to spread out. Specular reflection is when the beam just simply continues on after being reflected at the symmetric angle. And again, specular reflection in image B here is very apparent when you have things like mirrors or flat, very, very flat surfaces. Diffuse reflection, as in image A, the light will get scattered in all directions, and so people at almost any angle looking at the beam of light off of the surface will be able to see something. Okay. Now, mirrors operate on specular reflection, and it turns out, because of the law of reflection, that you only need a mirror half your height to see your whole body. Because if you have a mirror somewhat close to the top of your head, the height of the mirror is somewhat close to the top of your head, that means the bottom of the mirror will be about at your torso, at your waist, and your feet are going to reflect up to that halfway point and then up to your eyes. So if you need to see your entire body, you don't need an entire body size mirror. You in fact only need a mirror that's about half your height. In fact, it can be just even slightly smaller, because the top of your head can come in and then get reflected to your eyes, and so you only need about half of this right here as well. Half of this right here. Right. And so, as a result, your mirror does not have to be your entire body length. There's a very special type of mirror that reflects outgoing rays exactly parallel with the ray that was incoming. So, for example, if I have a ray coming in this direction here, it will get, if the mirrors are constructed in this way, such that this is a right angle, okay, then the reflected ray will come off of your second surface at a direction anti-parallel to the ray incoming. This is what's known as a retroreflector. This is also a mirror that's often used in certain magic tricks as well. But one of the practical applications of the retroreflector are things like bicycle reflectors, and we left a set of retroreflectors on the moon that we can bounce laser beams off of and measure the distance to the moon, and therefore measure its recession rate. Okay, so we've done this. We can do this, no problem. Now, all of this brings us to Snell's law. Okay, so what is Snell's law? Oof. So Snell's law is a law of refraction. So reflection is when the light will bounce off of a surface and its direction will change. Refraction is when you change the direction of a beam of light, but not because it reflects off of a material, but because it digs into a material and propagates through it. So Snell's law is the issue of refraction, and there is a specific reason that light does this, and we will discuss that momentarily, but the basic idea is this. If you have light being propagated through one medium, okay, here, and that light hits a flat boundary between two media. Now, it doesn't matter what these two media are, okay. The light will then bend when it goes into the new medium. It will bend based on what the densities of the two media are. We measure the densities of the two media by what we call the Index of Refraction. So N is called the Index of Refraction. And N is just a measure of, or it's actually the ratio of the speed of light in vacuum to the speed of light in the material. Okay? So N is the speed of light in vacuum divided by the speed of light in the material. And the basic or essential idea is that the more dense your material, the slower light will propagate because there's more matter in the way. The light will bounce around off of the atoms and have collisions, and that process slows the light down. And so each medium will have an index of refraction. Okay? And it doesn't matter if the light starts in one medium and goes into the second one, or if it starts in the second one and goes to the first one. The process is reversible. Okay? Typically, before we get into the actual mathematics of Snell's law, typically what happens is that your very, very non-dense materials, of course, in a vacuum, the ratio would be 1, right? So the ratio would be C over C. In air, the air molecules, compared to how light behaves, the air molecules are so not dense in our atmosphere that light barely notices that they're there. So, for practical purposes, we say that the index of refraction in air is approximately 1. Okay, so for any of your homework problems, whenever you see N of air, you can automatically assume that's 1 unless stated otherwise. Water, depending on its purity and whatnot, will typically have a index of refraction of around 1.3. Different types of glass will usually have an index of refraction of about 1.3 up to about 1.5. So 1.5, if I plug in 1.5 for N and solve for V, right? So if I have an index, let's say equal to 1.5, and that's equal to C over V, and I plug, I want to solve for V instead. Okay, this is the same thing as C divided by 3/2, which is the same thing as 2/3 C. So if I have a material like a dense glass that has an index of refraction of 1.5, then the speed of light in the glass will be about 200,000 or 200 million meters per second, where the speed of light in vacuum is 300 million meters per second. So I would be reducing the speed by about 33%. Okay, just for example. But again, in a lot of materials like air, we effectively say that the index of refraction is essentially 1. And so, with that in mind, now we can talk about Snell's law. Okay, so Snell's law says if I let 1 be the index of my first substance, or the substance that my light is initially propagating through. Okay, sometimes we call this the initial substance, but or the initial medium. But what Snell's law says is that the index of refraction in the incident medium times the sine of the angle that the light makes with the normal is going to be equal to the index of refraction in the second medium times the sine of the angle that the light makes with respect to the normal. So what this means is, for this equation to be true, if N1 is smaller than N2, then that means that sine theta 1 must be bigger than sine theta 2. And if sine increases from 0 to 90, so as long as I go from an angle of 0 with respect to the normal incident to an angle of 90 initially in the first medium, then my sine increasing and decreasing is going to correlate directly with theta increasing and decreasing. So if N1 is less than N2, then theta 1 is going to be greater than theta 2. So what this means is, if my ray is in an incident medium that is larger than the secondary medium or the refracted medium, then the light is going to get bent toward the normal because theta 2 will be smaller. If the light starts in the more dense medium, then the light will get refracted away from the normal. Okay? So if N1 is less than N2, then theta 1 will be bigger than theta 2, and the converse is true. If N1 is greater than N2, then theta 1 will be less than theta 2. So that is Snell's law. Okay? That is Snell's law. Typically, what will happen is you'll be given N1 and N2 and one of the angles, and so you'll have to find the other angle, or you'll be given one of the indices and both angles, and you have to solve for the other indice. So those are the typical problems that you would run into when solving Snell's law type problems. Okay. But there's some interesting consequences. Number one, not all of the light is refracted. If you look back at these ray diagrams, if you were to actually do this with a laser beam, and you could actually trace out the laser beam, and let's say this was like an acrylic prism, a rectangular prism, and this was a truly flat surface, what you would see is some of the light would get reflected. And it would get reflected at this same angle. Okay? So some of the light gets reflected and some of it would get refracted. But the total intensity of the reflected beam and the refracted beam would be equal to the total intensity of the incident beam. There isn't any power loss. In other words, energy is conserved. Snell's law also has another interesting consequence. Okay, so look at this equation, and so imagine that N1 is at my more dense medium here, and N2 is less dense. So remember, N1 sine theta 1 is equal to N2 sine theta 2. But if my light beam would get bent away from the normal in this situation, okay, in the situation right here, if light would get bent away from the normal, what that would mean is if I had a light beam coming in at a slightly less angle than what's shown here, if I have a light beam coming in here, the refracted beam out of the material might be right here. Okay? So it would all just depend on what the values of the ends were. So this outgoing beam is clearly a larger angle here than this angle right here. Okay? And so as I let this beam sweep out, the outgoing beam is going to get closer and closer to the surface of the prism, and at the angle theta c where that occurs, that's known as the critical angle. So what we're saying is n1 sine theta 1 is equal to n2 times the sine of 90. But the sine of 90 is 1. Right? The sine of 90 is 1. So this critical angle inside the first medium can be found from this. And to actually find the angle, if you know the two indices of refractions of the two media, then you can take the sine inverse. Okay, and that gives you the angle at which this critical angle happens. And if you push your internal or your incident angle beyond that, you get what's called total internal reflection, where all of the light gets reflected back into the medium. Okay, this is a very common process, and one area of technology that it is used in is that of fiber optics. Okay, fiber optics are built such that when you send a signal into the fiber optic array, the total internal reflection guarantees that the light will simply get transmitted through the fiber optic cables and none of it will be lost and bounce out. Refraction has some very interesting properties. And one of these properties is what's known as dispersion. And so dispersion is when you shine light on a prism and it actually then splits that light into its individual colors or its individual wavelengths. Even though Snell's law holds, what it turns out is that Snell's law is actually slightly different for each individual wavelength. So each individual wavelength you can think of as having its own slightly different index of refraction. Okay, so light will get bent by a prism differently based on its wavelengths, right? And this is the whole idea of breaking a piece of light up into its spectrum. And that's what we have here. So it turns out that the visible light portion of the electromagnetic spectrum does not span a very wide swath at all. So if you go back to radio waves, microwaves, infrared waves, visible light, UV, X-ray, ultraviolet, or X-ray and gamma rays, all of those branches span at least a few orders of magnitude across the frequency and wavelength regimes. Visible light is the only one that does not. Our eyes are tuned for a very specific set of colors. And these colors stretch from roughly 700 nanometers at the red end down to 400 nanometers at the violet end. And there's maybe a little bit beyond those two numbers, but still, we're still within 1 power of 10, no matter how you slice it, when you're talking about the electromagnetic spectrum that we can see in the visible range. So what happens? It turns out that when you have light incident on a prism, and this idea of dispersion occurs, okay, purple light is actually bent more than red light, right? Purple light is bent more than red light. So red doesn't bend quite as far as purple light does, right? So even though they're both bent, the purple light is bent just a little bit more. So the underlying process or the underlying principle is that the shorter your wavelength, the more you get bent. Okay, that is the guiding principle. The shorter your wavelength, the more you get bent. And so this is why you can see the rainbow after the light has exited a prism, just as we see in this image right here, right? And you can actually calculate what the index of refraction is for a given color if you can measure very precisely what that color's refracted angle between two materials are. Okay? And again, your red light is going to get bent just a little bit less than your purple light, and this is what causes things to spread out. Nowhere is this more dramatic than when you actually see a rainbow. So what's happening when you see a rainbow is you have sunlight coming in and it hits a water droplet, and the water droplet acts like a prism. And two things are happening. Number one, when the light is initially refracted into the droplet, the dispersion immediately starts, right? So here would be your red waves, here are your purple waves, and the entire spectrum is sandwiched between these two. And so your red bounces at a slightly less extreme angle and therefore gets reflected this way. Your purple is refracted or reflected at a larger, more extreme angle, and therefore its beam comes out this way. And this is what causes you to see a rainbow when the sun is at the appropriate angle in the sky and there's enough moisture in the air to have a lot of water droplets. So when you have enough water droplets and the sun is at the right angle in the sky, multiple water droplets give you the continuous full image, right? So one individual water droplet's not going to be enough. You need lots and lots and lots of water vapor in the air to get these types of images. But the sun coming in from essentially, a uniform rays of light are coming in other words, and hitting these water droplets in a direct line, or at least along parallel lines. What that means is when these parallel lines of rays come in from the sun and hit these water droplets, they're going to make a semicircle. And because you only see the rainbow when the reflection is just right, when the reflected angle or I should say when the angle of incidence of the sun coming in is just right, will you get this situation. And so these parallel rays coming in effectively give a spherical or circular, if you will, way that the rainbow can manifest, given that they can only disperse at certain angles. So I don't know if that sentence makes sense, but if you think it through, it should after some thought. You can think of a giant sheet of water particles, and the sun has to be at a specific angle to produce this, so only some of those particles are going to be involved in the refraction process, and it's those that are going to be equidistant to your eye effectively, and the only way you get that is with arches. You won't get equidistances with squares, in other words. And so the reflection and the dispersion that happens has to be circular, and therefore you get circular rainbows. And something very interesting to note when you have a double rainbow, as in the image out here, number one, inside the inner rainbow is usually much more vibrant, and in between the rainbows it can be a little hazy and cloudy. And then number two, the outer rainbow is almost always dimmer, and the colors are reversed. So on the inner rainbow, you'll always go red on top down to violet on the bottom, and on the outer rainbow, you'll go red on bottom toward violet on top. So that is why we see rainbows. So in the next video, we will cover some of the issues of Huygens principle and polarization. So stay tuned.